Okay, picture this for a second. You put a pot of water on the stove to boil, right? You turn up the heat, but instead of getting hotter, the water starts to freeze. I mean, that sounds completely impossible. A total violation of everything we think we know about heat. But what if I told you that in the really, really strange world of physics, something kind of like that can and actually does happen?
So yeah, that's the big question we're diving into. Can you heat something up and make it colder? It's a question that really cuts to the heart of how we understand energy and temperature. And believe it or not, the answer is yes, at least under some very specific and, let's be honest, very weird circumstances.
So on the left, that's our world. Our everyday intuition. You add heat, temperature goes up. Simple. But on the right, that's the paradox we're talking about today. A world where you add heat, you add energy, and the temperature actually goes down. And this isn't science fiction, folks. It's a real observed phenomenon.
Now, the official name for this bizarre behavior is negative heat capacity, or NHC for short. And it is exactly what it sounds like. It's a property where a system, when you pump energy into it, instead of its temperature going up, it's actually forced to go down. It's just wild. So where on Earth, or maybe off of it, does this even happen? Well, it turns out NHC isn't just some theoretical curiosity. We've seen it in some of the most extreme environments you can possibly imagine. We're talking about massive astrophysical systems like star clusters, all the way down to the tiniest atomic nanoclusters, and even inside the superhot plasma of fusion reactors. In places like these, the normal rules of thermodynamics, well, they just don't always apply.
So we know negative heat capacity exists, but why it happens, that's still a really deep puzzle. But a brand new paper, just out in May 2024, offers a really fascinating new clue. And it points the finger at one of the absolute weirdest parts of reality, the quantum world. The researchers think negative heat capacity might be tied to this idea right here, quantum non-locality. You've probably heard of it as spooky action at a distance. It's the thing that made even Einstein scratch his head. It's this idea that two particles can become entangled, linked, and then influence each other instantly, no matter how much space is between them. So how in the world do you even test an idea like that? Well, the scientists built a mathematical model, and they used these tools called non-local kernels, which basically let them translate the abstract weirdness of non-locality into the language of thermodynamics. It's a way of describing how a particle is influenced not just by its neighbors, but by things happening far, far away.
All right, so they've got their model, now it's time to test it. The researchers applied it to two different quantum systems to see if it would actually predict this strange negative heat capacity behavior. You can think of these as two key pieces of evidence in their whole scientific investigation. Okay, first up, a low-frequency quantum oscillator. Just try to imagine a tiny, fundamental particle just vibrating at the quantum level. And this isn't just a thought experiment. These little oscillators are super important parts of real materials, like certain kinds of superconductors. And check this out. This graph is straight from the paper, and it is the smoking gun. The bottom axis is temperature, and the side axis is heat capacity. Look what happens. Right after absolute zero, the heat capacity just dives deep into negative territory. Their model, powered by this idea of non-locality, actually predicted NHC. It worked. So for their second test, they looked at something a little different. A single particle stuck inside what's called a quantum well. It's basically like a tiny one-dimensional box that a particle can't escape from. It's another one of those fundamental building blocks in nanoscale physics. Now, in this second case, their non-local models spit out another totally bizarre result, something called a negative density of states. Okay, in simple terms, it means as you pump more energy into the system, there are actually fewer available quantum states for the particle to jump into. It's like climbing a ladder where the rungs start to vanish the higher you climb, just backwards. And here's the kicker. This negative density of states, this disappearing ladder, it provides a totally different path to the exact same conclusion, a negative heat capacity. So that's two different quantum systems analyzed with the same model, both pointing to the exact same strange thermal behavior. The evidence was building up. So, predicting negative heat capacity is a huge deal. But the model, it didn't stop there. It hinted at something even bigger, something that seems to challenge one of the most fundamental rules in all of physics. Take a look at this graph, also from the paper. This one shows entropy, the universe's measure of disorder, plotted against temperature. And as the temperature goes up, the entropy, the disorder, actually goes down. The system becomes more ordered as it gets hotter. This is the complete opposite of everything we're taught is supposed to happen. I mean, the contrast here is just staggering. The second law of thermodynamics is supposed to be this ironclad rule of the universe, right? In a closed system, things always get more disordered. An egg never unscrambles itself. But this new model, based on quantum non-localities, suggests that, well, maybe in these tiny systems it can.
This whole idea of decreasing entropy immediately makes you think of a famous thought experiment called Maxwell's D-men. The idea was this tiny little being could sit at a gate and sort fast hot particles from slow, cold ones, creating order out of chaos and breaking the second law. For over 150 years, it was just a puzzle, but this new research suggests that quantum non-locality might be acting like a real-life Maxwell's D-men.
And the authors of the paper, they totally lean into this incredible idea. In their conclusion, they wrote, probably there exists some ordering processes, which are characterized by decreasing entropy. They're basically saying the universe might have these natural built-in ways to create order from chaos, all powered by quantum mechanics.
So, what does all this really mean? This research, it's not just about some weird thermal property. It's about building a bridge between two of the most fundamental and, frankly, strangest parts of our universe.
So let's just quickly recap the story here. We started with this deep mystery of negative heat capacity. We found a clue in the weirdness of quantum non-locality. We saw the evidence from the models of oscillators and quantum wells, and we ended up with this mind-bending implication that this could challenge the fundamental laws of thermodynamics itself.
The big takeaway, the thing to really remember, is this. This paper suggests that the spooky action of the quantum world can have a direct, measurable effect on the big picture rules of heat and energy. It's saying that quantum mechanics and thermodynamics, two fields that can feel worlds apart, might actually be way more connected than we ever realized.
And that leaves us with one last, huge question to think about. If something as fundamental as quantum non-locality can reach out and seemingly bend the ironclad second law of thermodynamics, what other sacred laws of physics might have their own hidden quantum loopholes just waiting to be found? It really suggests the universe might be even stranger and more interconnected than any of us ever imagined.